again, thank you for joining us. This session is Spike2 Graphical Sequencer. As you can see from the screen here, I'm using 1009B. We've made some improvements just recently. Some of these improvements have been due to possible fixes or changes we've discovered would be useful during these training sessions. In fact, we had another modification made to Spike2 this morning just to change the color of the background for the graphical sequencer so you could see more easily some of the icons I'll be placing. Right, so we are running this once again live, so there may be problems, so please bear with us. Hopefully it won't be quite as serious as it was the other week with the internet issues we had. Right, so I've gone through the sampling configuration. So sample, sampling configuration, from the channels tab through to sequencer. Here we have a choice of the original text sequencer. So this is a set of commands that, or a program that you or I would write, and ultimately at sample time, that is sample start, we would load that into the 1401 so it can act in real time, as opposed to the program working at the computer, which then would be delayed somewhat by Windows, it not being a real-time system. So this sequencer lives inside of the 1401. That means we have much greater control over timing of everything that goes on. Now, if I show you one of those text sequences, you will understand a little about why the graphical sequencer is rather nice to have. Here in the text sequencer, you can see a delay command, and that is followed by a variable which we call del_t. There's a table command, which is like an array that we're loading with information or gathering information into it, say from data points captured in a channel or times of events. Diglow as a command into a table index we're addressing, etc. It's rather difficult to understand in this rather low-level code. So we have implemented the graphical sequence editor, and this ultimately will write the text sequencer for us. Okay, so we'll have a look at the output in a little while. You shouldn't be concerned about this, the writing of the text sequencer, because that's all done for you in the background. And so the graphical sequencer, in effect, is loaded into the 1401 at runtime. Writing as text sequencer can often help you develop your own sequences. And that's sometimes required because of more critical timing issues you might face. But we'll discover those as we work through the graphical sequencer. Okay, a couple of things to mention here. The minimum instruction. Now that sets a memory size inside of the 1401 for this program to exist in. Now, before a couple of versions ago, it wasn't Spike2, it wasn't possible to update the sequences on the fly, that is, while you're sampling. Now it is. Now, so if we change the graphical sequencer or upload a new text sequencer, they may have grown in size in terms of the number of instructions or number of commands that it contains. Therefore, we have to make sure that we have enough room to accommodate this larger file being uploaded. So for safety's sake there, I'm going to set it to say 1,000 instructions. Now that may not be enough ultimately for a graphical sequencer due to reasons that I'll show you a little later. Table space isn't so important, well, isn't important for the graphical sequencer. That's for the text sequencer. But certainly jump control may be very important to you. We have three options here: keyboard and control panel. That basically means anything can control the sequencer. This means that we're going to set labels, ABC, 1, 2, 3, characters of that type are going to be set to start sections of output. Okay, so if we click on the keyboard into a data file, then 1, 2, 3, ABC will start the appropriate section. We could also click on what is called the control panel, which is seen over here. This would have buttons next to it, depending on, and how many buttons depend on how many states or sections have been specified. You also have script control as well as part of the keyboard and control panel. But as we go down through the list, you can see that it's only the sequence control panel that may control the outputs, or it's only script commands. So you could fully isolate this control to a script or to the control panel. Very critical, the graphical sequencer time resolution. Now, as a program running in real time inside of the 1401, each command takes exactly 1 millisecond in this case to execute and move on. That means that if we had a sequence running from the start of sampling and we got to 60 seconds into recording, I could, in theory, tell you exactly which line we got to in the sequencer if we had a loop. Because everything takes exactly this amount of time. Now, there are some commands that have a certain variation on that, where they're preparing to create waveforms, for example. But most commands, the majority of commands, will take just this time. Now, 1 millisecond may not be fast enough for you. Imagine sending out a digital trigger pulse. You want it on and then off in 0.1 of a millisecond. Well, since the command to say go on takes 0.1 milliseconds, the command to take the digital signal down to 0 again takes 0.1 milliseconds. We can't do that if we have 1 millisecond resolution time. So we're going to have to improve on that. 0.1 millisecond, 0.01 milliseconds perhaps. The faster you run the sequence, the more pressure you're putting on the processor inside of the 1401. And although they're very fast, it's better to do decent housekeeping, making sure that the sequencer is only running as fast as you need it to for the outputs that are required. I'm going to set this back to 1 millisecond, but we'll go much faster later on. Down at the bottom here, sorry, I should just mention this, show time in milliseconds in the graphical editor. Rather nice for a lot of short outputs that you want to produce. I'm going to leave it in seconds for the moment because I want to handle longer sections to begin with. Down at the bottom here, we have the choice of digital and analog outputs. So with a micro on the analog side, you would normally have just 2 outputs, DAC 0 and DAC 1. Now, the newer Micro 4 has the ability to accommodate an extra 2 analog outputs on the rear panel, and that's a build time option for you. A Power 1401 could have a top box with an additional 2 or 4 analog outputs as well. So we could be controlling 8 waveform outputs with the Power 1401. All 1401s have the same number of digital outputs. Now we're looking at the high bits here, starting at 8 through 15. These are the ones you're probably more familiar with, the digital outputs on the front panel and digital inputs on the front panel too. Now the rest of those, and included a mirror image of the front panel connections, are available on the rear panel, as well as a further 8 low bytes, low bits, which will are sent out as a set. That is, you're sending out codes rather than individual triggers. Right, and over on the right here we have the Dac settings. So matching the 1401 input here, we've got a full scale of 5 volts in this case, and no 0 offset. But there's no reason why we couldn't, for example, be controlling a stimulator. That stimulator would see a 5 volt input as 100% output of the stimulator, or let's say it's 78 millivolt output at the stimulator. Okay, so we would set 5 volts is equivalent to 78 here. So we're setting a scale and an offset if necessary. Anyway, keeping it simple, full scale at 5. Now, absolute pulse levels. Well, this is used when we want to add a pulse, a shape, a ramp, a square wave, sinusoid to the analog output track, and we want to keep the absolute value. We say 5 volts peak to peak, and it will be 5 volts peak to peak. If we put another waveform or shape underneath this, then with absolute levels, the sinusoid, the ramp, the square wave stays at 5 volts. If that's not selected, the voltage is sum. Okay, so that's what absolute pulse levels are for. Right, now I've cleared everything out so far. So let's go and have a look at the graphical editor. So you see it's a blue tram line at the bottom of the screen here, and it shows me that this section, and this is one of 27 sections, is 1 second long. So there's 0 and there's 1. Now before I go on, I'm just going to cancel out of this, say OK here, and just show you that we added this morning application colors, the ability to change the background. Let's go to black, and the foreground meaning the waveforms and the titles, to white. And we'll come back to configuration to graphical editor. Okay, so this should be easier for you to see. The window is stretchable to a degree. So if I can make it any larger, no, you can't go any larger on the x-axis there. Right. So I mentioned the blue tram line. Because I'd selected 2 digital outputs and 2 analog outputs, you can see them all shown here. DAC and dig, okay, digital and analog. If I double click here, I can zoom in on the channel, and I should then be able to, once I click on the label there, I should be able to give a different label, so stim hash 1. No, I can't do that hash 1. I'm limited to the number of characters. So SG hash 1, double click again. Dig could be TMS, for example, is one type of stimulator. The other as electrical stimulator. So that does make it so much easier to keep a track of which output line, which output signal is controlling what. I mentioned 27 output sections. 26 labeled A through Z, and initial. Initial is special. It runs as soon as we start sampling. So if you really do want to have a stimulus output to your prep at time 0, or very close to time 0, initial is the way to do it. More often though, this section is left blank and used as a halt state. So I would put in a key H or S, and when I press that, when the sequencer calls it, or when the control panel S button is pressed, then this initial state with no outputs will be called. And since it's not told to go anywhere else at the end of this 1 second of time, then we really have stopped the sequence. For some people, using such things as talkers, then this initial section is really quite important. Because this runs at start time, we can put in, say, a digital pulse at 50 milliseconds, for example, and this would go off to trigger, say, a Delsys Trino system to say, now send us data. That means that with the talker, we can then align the incoming data from the DELSYS system with the known 50 millisecond time offset in the Spike2 document. So we've got a common, as it were, a common start, a known start for the talker, after which the drift correction will take over. Okay, so as you can see, I've placed a shape on the screen, and I've clicked and dragged it off the screen to delete it. Let's see what we can do with the analog side first. So double clicking in any one of the sections, a square wave as you've just seen, setting a size. Now that's the full range of my ADC, but if I set it to 2.5 volts or units, depending on the scaling that I've applied to the DAC outputs, then the graph updates. Start time and the length of the pulse. Now, if we try to set this to 0 as a start time, we get an error because we can't prepare everything for that pulse to go out. So we need to move it a little further in to the sequence, and that time can be much less if we change the resolution setting to be faster. Okay, so there's a square wave. We have something quite similar here, a -5 to start, but a change of 1 volt. So this is going to repeat, or rather going to change its amplitude per repeat. Unfortunately, unlike signal, from where this graphical sequencer came, I haven't got a simulation button, so I can't see this doing its steps in this view. The next item might be a ramp. Well, a ramp from 0 to 5 could be negative values, anything you like, and set a length. We could combine that perhaps with the square wave. So let's change the ramp now to 2.5 and then add another ramp on the tail end where we start at 2.5 volts and we go to 0 but over a longer period, like so. And finally, we have a sinusoid. And if we set this to 5 volts again, we can change the frequency. Now, this all depends again on the resolution that we've set as to the fastest rates we can achieve. But so it's quite visible to you. There we go. Now, setting the center here gives us an offset. Okay. We'll then match that by clicking on the base output line and setting that to 1 volt. Okay, so there we go. Setting the frequency period, the phase, etc. I'm going to throw these away and set that back to 0 for a second. I don't think I'm going to use this output for anything real for the time being, but hopefully that's described to you some of the shapes that we can add in. If I had many outputs or many sections that I wanted based on this set of outputs, though, I could copy everything from this state, initial, to another. So if we went to C, for example, I'm copying the digital and analog lines, I'm copying the section length and possibly the control track. Now, the control track is important because that contains items from the bottom half of the palette. So wait for conditions, branch if conditions, variable arithmetic and markers as well. So I'll just click on that and you'll see A, B, and C now have exactly the same data in them. Okay. Right, let's go to A and throw away what we have here. You've also got delete. Okay, and we're going to now look at these pulses on the second row. I think starting with this one, which shows us, say, 5 pulses, increasing amplitude. Okay, starting at, say, -1, so we can see there are actually 5, stepping by 0.2, there we go. Right, so you're building a list of DAC outputs. DAC 0 then told to go to DAC 0 at 0, then DAC 0 told to go to -1, a delay, then go to the next step. So you're describing the points of change here. Now, many people want to get lots of digital outputs. Now, this train of square waves I can put onto an analog line, or I can put onto a digital line. That's not true of something like a ramp, which can easily go onto an analog line, but can't go onto a digital line. And that's, of course, because digital is purely 0 or 1. So in our case, 0 or 5 volts, on or off. Let's put the digital pulses there, and we say that we want now 500 of them. We've got a length of 1 millisecond, and we want this at 50 hertz, 500 hertz. We've got lots of pulses there. Okay, so I've just shifted them across. I'm now going to increase the length of this section from 1 second to 100 seconds. So there's my digital output pulses. Now I'm going to try very hard to put another set at the end, and we're going to say there are 1,000 of those, and the length 0.01, interval, etc., and joining them up. Okay. It's a mess. It's rather difficult to see. There is a limit to the number of pulses there can be set in, can be output in one set. And as you can see, I can't see where these join up. So far better to throw away all of that and reduce this length, the section length, to something like 0.01. At which point we would place one digital output on the screen. No, I'm going to have to increase the resolution there. Okay, Graphical Editor. Okay, so there's no errors anymore. You saw the red, I hope, coming up. In fact, I think I'll put that back to 1 millisecond. It's a good talking point. So section 8. Usually you have a small dot on just underneath the blue line, and certainly you have a report of timing faults at the top of the screen. That means that the code isn't going to do exactly what you've asked for. So two things possibly colliding in terms of the commands used, trying to make them happen at the same time, and they can't in a number of circumstances. So here I need to give more time to the sequence to execute the commands in this case. So hence the 0.1 milliseconds, and the errors disappear. So the idea here being that we're going to output 1,000, 10,000, 1 million pulses using just one output here, but then tell the system, the section, to repeat itself. Now, if I just go back to section A with repeats once, that would go on indefinitely until the sequencer is told to go elsewhere. Again, either through a key press, script control, or through the sequencer control box there. So we must calculate the time from this rising edge through to the end of this section and back around again to get the frequency output that we want. This also makes it much easier to add, say, markers. I'm just going to the bottom of the palette here and adding a marker. So every time I'm going to have to change the resolution once again, but every time that this pulse goes out, a marker with code Z will be produced. So this can mean that when using a digital marker channel in your sampling configuration, we're recording the marker to say it happened, and it happened at this time, rather than having to output the digital pulse and feed it back into the system. Okay. Now those marker codes can change. For some people, they wish to place multiple markers. So let's put this back to something more reasonable, 0.1. So we've got a marker 1 here, followed by another marker corresponding to another square wave here, and we might call that marker 2, etc. So you can have an indicator as to which pulse was sent out. Okay, right. I'll come back to the arbitrary waveforms, which of course can only be applied to the analog lines. But that too is one of those icons that can only be added to the blue bar at the bottom of the screen. That's because we could be talking to DAC number 8 or DAC number 028 inclusive. With this item. Anyway, I will come back to that in a little while. Now, the next items down at the bottom here are wait for, branches, markers you've seen, and array arithmetic. Okay, so I'm just going to clear this out by loading in another configuration. Okay, so this time in the sequencer, you see I've restricted this to just an analog output and a digital output. Graphical Editor, and this time I've kept it a little cleaner by adding some array arithmetic to the bottom of the screen here. So I'm setting a variable number 1 to 0 at this time point. Now I've spread these icons out a little so you can see exactly what's going on. Much of the time you would keep them very close together if you needed, if you're working with say time, for example. Now here I'm setting variable number 3 to the current time into sampling. I'm then setting variable 2 to the current time. Then I'm subtracting, should be subtracting one variable from another. So I've zeroed things. That was an attempt early on today to try and reset the time into sampling for something else I wanted to show you. But here it's not going to work in quite, well, it does briefly work, but it doesn't work in quite the way we would expect. And that's where extra commands within the text sequencer would make things easier. Okay. Now we often don't expect people to use the graphical sequencer and lots of variables. It's not really tuned for that purpose. But I'll show you what we can do with a variable, and that is I'm sending out a digital pulse here, and at the digital pulse transition time to high, I'm adding to variable number 1 a value of 1. So this is going to increment. Here, I'm setting a wait for again, and that's when time is reached. And so for that, I've given it 15 seconds. So when sampling time has reached 15 seconds, then continue on. So on a key press A, time for this section starts. We run through, it gets to about half a second. In fact, it gets to 0.4 of a second. It sets the variable or adds 1 to the variable already. It then sets this digital pulse to go high at That's that time. At 0.43 seconds, we're sitting there and waiting for this time to be reached. And that's going to be 15 seconds. So this first pulse is going to be quite long. And at the end, at the transition back to 0, we're going to see the marker here, or sorry, the variable set to the current time. So that's variable number 2 set to the current time in sampling. It'll become a little clearer in a second when I start sampling. So let's run now. In fact, yeah, run now. Okay, we'll get rid of that. I'm going to run a little script here. And we start sampling, and immediately I go to A. Now the keyboard marker shows us that the A character is pressed. That first pulse of the A section has gone out. Now it's waiting until 15 seconds. Here we go. And we should see a change, yes. So the 15 seconds sample time was matched. And then we had a little bit more time before we finished off the pulse. And then we've gone round again through that section, sending out the same pulse again and again and again. But since the 15 seconds that we specified as a sample time has gone, then all of these pulses are only as long as specified here. So 0.1 of a second. But notice I'm seeing a count here. So every time we see a pulse, I'm reading out a count so I can know how many pulses I've sent out throughout the recording. And that same variable can be used within multiple sections, either reset or just accumulating a count of every stimulus that was applied. The script here is using a simple command here. So we are sample seq var. So sample sequencer variable number 1. Tell me what it is. Tell the 41 to give you that variable number. Now, as an integer, it's come back 86, 87, etc. And then I've also asked for the timer as well, the time into sampling. And then I've rounded it somewhat. So you can see we're just at 109, 110 seconds there. So you can get some basic feedback with a simple setup like this and an info window, which is just convenient to display the data and the information you want to show. Now, I think you noticed earlier that I could access the sequencer while sampling, which means I could set that back and increase the length of the pulse. Is that going to show up? And apply. Right. As soon as I press apply, the sequencer stops. Now, the reason is we can't really carry on from where we were because things have changed. So we're asking you to start the output again. So if we press A again, this time the long pulse won't exist because we've already had that 15 seconds that I wanted to wait for. That's already gone. You can see the length of the pulses has increased to the 400 milliseconds that I've specified. Okay. Right, now, what else have we got here? Let's go to Halt. Section B, C, right. Looking at C here. Now, from the bottom of the palette, I've pulled up an icon. I'll put another one over here. And this will say, this will give me a choice of a fixed delay, a random delay, Poisson delay, waiting for a digital input to be high, low, waiting for a waveform channel to be above, below, within or outside of levels, waiting for a next event. So we're waiting for perhaps a trigger to come from a stimulator to say it fired before we can start a clock timing again to control another device, or just react as quickly as you can to that next event by sending another signal or waveform out. Time reached. Well, you've discovered that already, that 15 seconds into sampling that we'd set up originally. I'll wait for the cosine, the output cosine, to reach phase 0, and then we've got a lot of variable arithmetic. So we could be counting up, counting down, comparing variables, and then decide what, and then move on through time. So these are all wait for a condition items. That's compared to the next palette item here, which is branch on condition. So here we have branch on probability. Again, whether a digital input is high or low, the waveforms inside, outside, within, sorry, above, below, etc. And again, the variable arithmetic. So on a condition, let's say probability, that this guy with a 50% probability either continues on in time or goes to another section. Okay, so time passes, we hit this marker, decide, flip a coin, 50-50, we're going to continue on, or we're going to go to the Z section. If we put another icon like that in there, and we could make this with a 25% probability to go to yet another section and so on. So you could keep building up this this branching and get a balanced probability if you try to go to one of n number of other sections. Okay, I'm going to clear that out. Get rid of these. Okay, here I've chosen an event burst to look for. So what I've specified is the channel number when it comes to the data document to monitor. So channel 3, if it's analog, then it could be port number 2, but it is the channel number in the data document that's important here. I'm looking to find 3 intervals where they have no greater time than 0.1 seconds between them. Now I've left that fairly large because I'm just using a trigger switch here to produce the output, and the switch isn't that easy to operate. If this were a wave mark channel, so your spikes and spike sorting, if this were digital pulses from a window discriminator, then these maximum times would be, I would suggest, much smaller. You might also want to consider a burst as being just 2 events as well. Okay, so let's try this. We're going to jump to section C when we start sampling, and this will only operate once for every time we press the C button. If we wanted it to repeat more than that, we can either specify the number of repeats, or we could tell the system just to go back to itself. So let's just halt after 1. Okay, and we can close that. We don't need to make any changes. I'm just going to test my trigger input. So I'm looking at channel 3 here. So that should be this lead here. Okay, so at the top here, you should be seeing these event markers. Okay, nothing happens until I press C. That section has caused the stoppage of all of the digital outputs because I haven't set those to continue in any way or be reproduced in that section. Digital markers come through. That is not considered a burst until we start getting faster. And then when we've matched the event burst parameters at this point here, there are actually more markers and more events in there than it might first appear, then the sinusoid was sent out. So that is an event burst. And obviously, a very short period of time, that's less than 0.1 seconds. Okay, so that was an event burst. Before we let this continue on, let's have a look at some of the others there. I'm going to slow down time here. Let's see what we've got in B. So here we've got a waveform with a changing amplitude. So that's starting at -5 volts with a change of 1 volts. And this section will repeat 11 times. So here we go with B. Now we see every time the section loops around, we will get a different output. Once again, we could add markers to the, say, leading edge of those pulses. We could add a marker just to say that it actually fired now, because when I press B, that takes time to get to the 1401. That is not the time that we started that section. So it could be delayed by a few milliseconds. So to have an accurate marker to say this is actually the beginning of the section would be useful. And certainly to label, as it were, the pulses going out. Right, let's have another look. So there's a section. Let's change that because I threw in an extra event there. So we ran over the maximum, we wrapped round. So let's make some changes. So we're going to change by 0.2 this time. Okay, and apply and output B again. Okay, so now you can see it's much smaller in terms of amplitude change. Okay. So online control of the sequence, but beware, you will have to stop the sequence by just the fact that you've made modifications and applied these, and then restart. Now, if you're proficient with a script, then it's possible to take variables from the graphical sequencer, certainly from a text sequencer, keep them within the script and reload them back into the sequence. So you can pretty much start again where you left off. All right, so that's a waveform change, C and D. Right, so I'm just going to fire this off. So no change. We just want to see what happens. Okay, right, so I'm going to zoom in on that. Now we told this ramp to start rising from here, and we told it its target position, that was going to be 5 volts. But here, I threw in a fixed delay. Okay, now that fixed delay is hit on this line, and we're waiting for half a second. Now, if I look here, it should be half a second. Why? Why didn't I get a plateau? Why didn't I see a notch in this ramp? You see, we've gone all the way to 5 volts here. Well, there are some things, some outputs, just like the ramp, that we can say, go, this is your target, go to it, and it'll just be left alone. We're not interrupting it. A long time ago, we had to calculate each step and work through that way. These days, it's, as I say, a slope, a target has been calculated, and it's fire and forget. Okay, so we're not interrupting the output here. Right, so there's that. A fairly new feature, not within the graphical sequencer, but a command in the text sequencer does allow us to fire off and forget the digital lines, or at least I can say a digital line, thinking in terms of a camera system. If you wish to trigger an external camera, we could use the clock output of the 41. We could use a dedicated digital output of the 41, all driven by the sequence. But now with a new text sequence command, we can say to a digital output, fire at 30 hertz, and then forget about it. It'll just keep doing that until we tell it to do something else, much like the ramp you've seen here. Going back to the clock output, I'm sure some of you have wondered what the clock is on the front panel of the 41. Well, that gives a pulse out every time there is an instruction executed within the sequencer. So it runs, it will output pulses at 1000 hertz in this case, because I'm running the sequencer at 1 millisecond resolution. Okay, and of course that rate will change if I change that resolution. Right. Okay, so I think we should get to waveform output. So I promised to deal with this, the arbitrary waveforms. Let's find a data file. So if we take something like demo, and we could take something over here that's going to be quite visible. That's a bad sample rate, but it's still a good example. At least it will stand out in the graphical sequencer. So what I'm going to do is go to Sample, Output Waveform. And from here, I can select the channel or channels that I wish to output. If I close this, duplicate this channel, do a channel process just to offset everything, and with a time shift, add. Okay, so you can see they're slightly different. I would have to go to select the channels before they will be visible here for us. So close, sample, output waveform. Now I have two channels, and I can select the range, X low to X high, or specify a time by typing it in, or use vertical cursors. And I can then, the DAC outputs are then enabled for me. Well, more than one DAC output is enabled for me. Okay, the two channels are sampled at the same rate, 100 hertz. Well, this could be 1000 hertz, could be 10,000 hertz. This data is held in memory. Okay, so we start playing out that memory when we trigger a waveform output. Now, these waveforms will be played out at the highest rate of the set, of any channel found in the set. Okay, so the next step is to add to online. I'm going to label this and give it a key. Now, in this case, I'm being careful not to match the keys used for the waveform sections, because which would win? If we called everything A, is it the sequencer section that wins, that is plays first, or is it the output waveform that we've got here playing first? So to keep the mind clear and hopefully eliminate any errors, the key that I'm associating with the waveforms is, say, 1, 2, 3 versus the ABC of the sections. Okay, so let's add that and close. Now you'll see in the sampling configuration, under the play waveform section, that there is the data that I've just added from the data file. Okay, so it's waveform demo. Now, if we were to do this and want to store it in the configuration, we might separate it. The data. Sorry, start again. We might want to separate the data points from the data file. That is, take an image of the section of waveform that we want to play out and put it into the configuration. If not, we would always have to go and be able to find the data file from which this data came from. And that's where we have a convert button. It's made me realize that since I'm still sampling, that I can't go any further with this. So I'm going to just stop that and sample, output waveform, repeat exactly what I did, add to online. I'm replacing what I had there. Okay, and close. This time in the play wave section, you can see I have the convert. Convert between using the source as a data file or using the source as an array of a set of values held within a configuration. Putting it into memory, in other words. Okay. From here, we could also say that we want to link different sections together. And so if I had two waveform output sections, one would play after the other. I can also increase the speeds, as you can see, and tell it how many times, how many repeats I want of that section. The idea of linking two memory sections here is useful when we want to play out long waveforms. So imagine we've exceeded the memory of the 14.1. That is a megabyte for many people inside of the 14.1 micro, now 32 megabytes or a gigabyte in the Power 14.1. There are certain memory sizes that we can fit, certain waveform sizes we can fit within each 14.1. There are multiple sections or segments, memory sections as well. So if we wanted to play out, say, a month's worth of recording, okay, it's simply not going to fit into memory. So using a script and two empty memory sections, we could play out one section and then link it to the next. As the second section is playing out, we fill the first section with new data, which is the next part to play. And we simply link these two sections end to end. So like an infinite loop. Right, so that's just a little extra there. Okay, so we go to Sequencer, to Graphical Editor, and we'll choose this time section E and arbitrary waveform. There we go. I'll set the length to something like 10 seconds, and you can see the waveform that we've produced or taken from the demo file there is now inside the output section to play. So once again, the marker goes onto the blue tram line at the bottom, not onto one of the analog lines. So we could now wait for a waveform to be above a level. Okay, so we'd have to specify which analog channel, because that's what this type of output or type of detection means. It's an analog channel, and it would have a threshold of, say, 2.5 volts. It's at 0.1 seconds, for example. Okay, and then as soon as that condition is matched, more time passes before we get to this item, which is our waveform output, and therefore that section should fire off 2 seconds, virtually 2 seconds after the detection. Now, of course, we could compress this. We could move the waveform right up to the detection time. We could make it easier to see here, setting this to, say, 2 seconds in width. Okay, there we go. And bring it close, but we can't put it at the same time. Okay, so there's a timing fault. So I'll need to shift that. No timing fault, no small red marker underneath these two items. So we're looking for a waveform to go above a level, 2.5 volts. And as soon as that condition is met, then this waveform will play out. Okay. Now, if I wanted again to get finer timings between the detection and waveform player, I'm back to the resolution for the sequencer. Okay. Right, let's find something a little better than that. So this time, instead of an event detection, I'm just going to play out a nice robust sinusoid. And this time, I'm going to put here waveform above and the 2.5 volts. Okay. Right, so that's all set and ready. We start. Remember, H2 the initial section is already run, and any of these with the keys set A, B, C, and D need to be executed by us. So it's C that we're going to detect the waveform. So channel 1, and then once that waveform is achieved 2.5 volts, then the sinusoid will go out. Okay, so on C, I'll use this button this time. We're now in the detection mode. So here it's saying wait for channel 1 to be above 2.5 volts. I've got a simple waveform generator here on a joystick. There we go. Right, so that's managed to fire it. Now we need a way of seeing it. So I'm just going to port that and add in another channel. So the waveform, just duplicate that. One now, start, C. We're in the detection cycle. Waveform goes above. There we go. And that's not going to happen again until we fire off C. Okay. So the same applies if we're going to set two thresholds to be, so the waveform has to be outside or within, and we can combine some of this as well. So that you might want to detect when you're outside of levels, and then start searching for a peak, for example. It's a little bit easier, well, it's certainly easier with a text sequencer, but items like that could be programmed in to the graphical sequencer. Right, now one thing I haven't talked about yet, and we're starting to run out of time, is the branching or control when not using these labels. So at the moment, every section that I've got here has a label. So A, B, C, and D. But I might want to show how section A then runs on to, or after 10 repeats, runs on to section B. Section B will repeat 11 times, and then we'll run on to section D. So they don't have to be in order. Section D will do its thing with a ramp before finishing after 1 second and heading to C. So I haven't planned to do this quite this way, but let's close that. Let's restart the sampling. Let's start, and we kick off A. There's our first pulse going out. Now remember, this was limited. We were waiting for 15 seconds to pass. So as soon as we get to 15 seconds, which is about here, we'll see a change to the low state, followed by now the pulses going out. Now this should only, I think, repeat 10 times before we go elsewhere. There we go. So we've stopped, we've jumped to another section. We didn't put any markers in to identify that the section changes, but you can, I hope you can see the different waveforms and signs playing out. There's the ramp. Now we're in C, which means if I change my waveform output, they're not quite achieving 2.5 volts. There we go. There's my sinusoid. Okay, so hopefully that shows you that how the sections come together, how they can be linked together, some of the variable arithmetic markers and the palette items for all of those waveforms and digital outputs as well. Okay, so I think we're about time now. Has anybody got any questions at this point? Has anybody got any examples that they'd like me to go through for the sort of work that they carry out? So I'll give you a short time to think about that and put that in the chat. Okay, I don't think we're getting any feedback at the moment. And unfortunately, I don't think Zoom tells us if anybody's active typing. Right. Well, I think that's it as an introduction. There is more I could say. If you want me to carry on for a little while longer, let me know. I could show you a little bit of the text sequencer. In fact, let's finish with that. Let's now output our sequencer as a text sequence. We call it test. I'm going to put it in training sessions here. So save. Okay. And now if I open same file. Okay. This is written out all of the code, which ultimately would end up inside the 1401. Now, if I can find the section which had the digital outputs, that would have been A. Okay, digital delay. This has been somewhat improved in terms of before. The description that the commands here would simply give you point-to-point changes. So dig out, go high, delay for so long, dig out, go low. If there were 500 pulses, it would describe each and every one of them. And it looks as though this has been put into more of a loop there. Loop calls, digital outputs, etc. All right. So we could take sections of this output and make our own sequence, or we could modify what's here, renaming things like the variable one, etc., with a real name, an understandable name for us. What else have we got? A good thing to talk about. Oh yes, right. Something like this. We've made it easier by putting in milliseconds or seconds or even microseconds and then a value. That's the delay time. And so the sequencer calculates how many ticks it takes for that time to elapse. Okay, so usually you would you would normally have put in something like delay 1000, meaning 1000 milliseconds, because that's the resolution that we've set. We then say -1 from that, as you see here, because that's the delay command itself taking up one of those clock ticks. Okay. And so that's a little bit of more detail. on the text sequencer side there. Okay, so from Tabitha, we have a question, which is, would it be possible to send a signal out that isn't periodic? For example, let's say I want to send out a train of 0.1 millisecond pulses where the instantaneous frequency between the pulses varies between 1 and 10 hertz. Yes, we've got lots of examples of that sort of thing. Linear frequency ramps. So we can calculate where the next pulse will be and play it out. But a lot of this requires the text sequencer because you haven't got the finer control of it. So let's just think what we can do for you now, right now, Tabitha, and that's let's go sequencer, sample sequencer there. Let's go to Graphical Editor. Okay, so we're on a next one, F here. Here's a pulse. Oh, sorry, that's the analog line. I want it on the digital line. Here's a pulse. Here's a pulse. Here's a pulse. And here's a pulse. Okay. So I'm describing very, very roughly, I'm describing a train of pulses with differing intervals. It would be much simpler to have a script load the text sequencer at this point with the times or delays between those pulses that you want to play out. But you could, with care, do what you want with the graphical sequencer here. I'm just trying to think whether I could do that a little more with the variable arithmetic. But that's the way I would go. Hopefully soon, we'll also have script commands built into Spike2, which will match those that are already in Signal. And those are to control the pulses. So if you said, if you calculated using a script the times of the pulses to play out, you calculated how many pulses to play out, you could then address the graphical sequencer, place the first marker, that is the digital output, and then subsequently place all the others using a script and save you a lot of time. But Tabitha, if you get in touch, then I can be more than happy to send you a couple of examples that do what you require. Okay. So I think from Tabitha again, I'm just skipping one chat. Can I call a random number generator in the text sequence, or would I have to hard code the intervals? You can call a random number. Rather, you could put something in here and have a random or a Poisson delay with it might be simpler to load into a variable inside of the sequencer the random number generated by the rand command of the script language. Okay, so you could do all sorts of things that way. Have a random intervals within limits, or follow a pattern, as you said, from say 1 hertz to 10 hertz. Okay, but again, I'll get back to you with some examples of that. Right, so Mia, is it possible to import a text sequencer file into the graphical? You're not the first person, you certainly won't be the last person to ask this. It's virtually impossible to do that. What we're showing you here is something that can be displayed graphically. There are so many cases in the text sequencer where it simply wouldn't make sense in this timeline display that we've got here. So I'm afraid, no, there is no easy way that we could put that in for you. Okay, Jessica, is there a reason for not being able to get the letters to come up to run the stim? Okay, but the letters didn't come up when I ran the last set of outputs, because section B was linked to A automatically, D was linked to B, and C was linked to D. And because I haven't initiated B, C, and D from the keyboard control panel of the script, then those markers didn't appear. So as far as the sequence of events are concerned, it was only A that started them off. Okay, but that's where we might use a digital marker. Say here. Now, where am I? Can I do this? A marker somewhere in here, just to put in A, B, or C, for example, at some time point into the section. So possibly at the first pulse out. Okay, I hope that answers your question, Jessica. Tabitha. Okay, Tabitha, thank you. Amir. Right, which line in the text determines the sequencer time resolution? That's usually right at the top. Now, when we get to the text sequencer, have we got any here? Let's cancel that. Let's just create a new one because we can. Sequencer document. First thing you normally do is set 1, meaning 1 millisecond, 0.1, meaning 0.1 millisecond, comma, and then the Dac scaling. So that's 1, 0. So that means no scaling at all. That's using the 5-volt range and no offset. So if we needed to do any scaling, these are the two items, scale and offset. These are the two items, and here is the speed. The next thing you want to do is probably halt. You don't want the sequence just running on. So you might put a halt in there. If you want something to be triggered off, we need a character. Capital G, lower G, dig out, 1, 2, 3, 4, 1, 2, 3, 1. That's a digital output pulse on bit 8. Dig out, 1, 2, 3, 4, 1, 2, 3, 4. That stops it. And then we can tell this to have a short delay, seconds, 1, -1 clock tick, and then we can tell it where to go next, and that is where we set a label. So that's equivalent to us saying connect section A in our graphical sequencer to another section here. In this case, it's a loop. So on a G press, this loop will output a digital pulse, have a delay of 1 second, and then loop round again. Okay, so we'll just very quickly try this. I just set this save. That seems to be all right. Usually my spelling lets me down here, but let's run this. The sequencer is now current. We'll start. I hope we've got everything connected. Okay, G. There we go. There's our pulses going out. If I put a label in here, and that's going to be H, and just like the graphical sequencer, I make current, it says online sequence changed. Okay, that stopped the sequence just as the graphical version applied stopped it. Hit G again, but this time I've got H associated with the sequence as well. That allows me to stop the sequence as well. And just in case, in the sequencer output, let's abort all of this. Let's go to the configuration. Let's set this to 0 and run now. Start. Outputs are happening, that's fine. I now wish to modify that sequence a little more. So where is it? Show. sequence 1. That's the current output. Let's just try and duplicate this just to increase the number of outputs, or the size of the file rather. Just make this a little different. Let's give it a different key and BB. This is all to show you that if I now compile, check the formatting, perhaps choose to see which line numbers are which, and this helps with your timing and taking away the number of clock ticks. And then I make current. The sequence is too long. You must stop sampling. That's because I didn't allocate enough space for the graphical or the text sequencer in the configuration. Okay, so I think that's a good moment to finish, but I hope I've answered everything. There's yep, just something from Marjorie. So I hope that's given you a thorough grounding, at least, on what the graphical sequencer can do, linking sections, and some of the finer points. And hope to see you next time, which thankfully is the last session I have to do next week, where we hopefully will put everything into one, running the sequencer, sampling data, doing some online analysis, offline analysis. And I'm hoping to poll you all and ask you what channels we should be adding and what sort of analysis you want to carry out all in one. Okay, well, until next week, thank you very much, and see you next time. Okay, bye-bye.